Physical cables transmit analog signals. As shown, a clean binary signal generated by a sender often degrades into a distorted noise wave. A microscopic voltage fluctuation or external interference can flip a single bit, corrupting the entire sequence upon arrival. To solve this, architectures rely on the OSI data link layer, Layer 2. Sitting directly above the physical hardware, it acts as a software shield. It takes the raw, unreliable bit stream from the wire and organizes those bits into structured blocks called frames. Computers cannot assume their hardware is perfect. They must use mathematically verifiable software protocols at Layer 2 to guarantee the accuracy of every message. To protect data integrity, Layer 2 relies on three core mechanisms: framing, flow control, and error control. Framing chunks the infinite stream of bits into discrete, manageable payloads by attaching specific headers and trailers. Flow control regulates transmission speeds, ensuring that a fast sender does not overwhelm a slow receiver. Consider this high-volume pipe. If a high-speed node blasts data into a device with limited processing capacity, the receiver drops the packets entirely. By contrast, this controlled stream matches the sender's transmission rate to the receiver's capacity, ensuring every drop makes it inside. While framing organizes the structure and flow control paces the delivery, error control uses mathematics to prove the data arrived perfectly intact. Parity checking is the simplest form of error detection, appending a single redundant bit to a data sequence. For even parity, the sender counts the ones. If odd, it adds a 1, ensuring the total count of ones in the final frame is always even. This method fails when multiple bits are corrupted simultaneously. If 2 bits flip during transmission, a burst error, the total count of ones remains even. The receiver checks the parity, calculates an even number, and completely accepts the corrupted data. Simple addition is insufficient to combat real-world interference. Engineers solve this by utilizing polynomial binary division. This flowchart illustrates the cyclic redundancy check, or CRC. It is the industry standard for catching transmission errors. Before sending a single bit, both sender and receiver must agree on a predetermined binary divisor, having a specific length of n+1 bits. Here, the sender appends n zeros to the data payload, then performs binary long division using the agreed divisor. The quotient is discarded. The remainder is the only valuable output. This remainder replaces the appended zeros, becoming the final CRC code attached to the data frame. The sender has bound the data payload to a specific mathematical polynomial. The frame is now verifiable and ready for the physical wire. This chart shows the receiver capturing the incoming frame, which now contains both the original data and the newly generated CRC. As shown, the receiver takes the entire incoming frame, data and CRC together, and runs the exact same binary division using the predetermined divisor. If no bits have flipped in transit, dividing the frame by the divisor will always yield a remainder of exactly 0. If the remainder is anything other than 0, the receiver instantly knows the hardware altered the bits. The receiver triggers an automatic repeat request, or ARQ. It discards the corrupted frame entirely and demands a fresh transmission from the sender. CRC detects errors with incredible accuracy. However, relying on retransmission creates severe latency bottlenecks, particularly across long-distance or slow network connections. The alternative to retransmission is forward error correction. Instead of asking for a new copy, the receiver fixes the corrupted bits locally. Because a bit only exists as a 0 or a 1, correcting an error simply means inverting it. You just need to know its exact coordinate position. To find that position, we use the Hamming code formula, which calculates how many redundant R bits protect M data bits. These R bits generate unique states for a clean signal plus every potential error position. For 7 data bits, the lowest R is 4. Those 4 redundant bits act as an internal coordinate system. They can pinpoint a single flipped bit anywhere within the final 11-bit frame. Redundant bits are inserted into the frame at index positions that are powers of 2, 1, 2, 4, and 8. Each performs a parity check for a specific, overlapping subset of bits. Bit 1 checks alternating positions. Bit 2 checks 2, then skips 2. The sender calculates the binary value of each R bit using simple, even parity based on its assigned subset. When a bit flips in transit, a unique combination of these overlapping checks will fail at the receiver. The sequence of those passes and fails generates a binary number that exactly matches the index coordinate of the broken bit. By weaving these parity checks together, Hamming codes elevate the raw hardware. The receiver surgically inverts the corrupted bit, bypassing the delay of retransmission. Whether the receiver verifies a frame via CRC or corrupts it via a Hamming code, it must report its success back to the sender. The baseline approach sends empty acknowledgement, or ACK, frames. This clutters the network and consumes bandwidth. Layer 2 optimizes this using a technique called piggybacking. The receiver delays its acknowledgement slightly so it can attach the ACK directly to the header of its own outgoing data frame. Piggybacking halves the communication overhead. It ensures that the constant mathematical error checking doesn't cripple the overall speed of the network. We've now traced the full life cycle of a data link frame, chunked from a bit stream, speed-regulated, mathematically verified, and acknowledged. The contrast between the chaotic physical wire and the highly ordered output of Layer 2 is absolute. Algorithms like polynomial binary division and intersecting parity matrices are the silent engines that make this transformation possible. The payload is then stripped of its Layer 2 headers and passed cleanly up to the network layer, ready for global routing. Without the rigorous, unseen mathematics of the data link layer, the internet would collapse under the weight of its own physical hardware errors.